Oh, hi. Welcome to pre-lab lecture for chemical kinetics lab. This is going to be a dry lab. What I want to do is go through some basic terminologies you need to have or you need to understand in order to complete the lab data sheet. I'll split the pre-lab lecture into two parts, or part one and part two. In part one, mainly I will walk you through example of determining the reaction orders in the rate law with respect to each reactant. I will split the screen into two. On my left will be the procedure, and on my right will be the whiteboard, my whiteboard. I'll be writing down some equations. Please have a pen and a pencil so that at least you cut to write down the equations. Allow me to share my screen here. I'm going to share the screen. Here you can see the whiteboard with the title Chemical Kinetics, the method of initial rate, constant and concentration. Here I have the handout, which is uh, just a PDF file of lab experiment on method of kinetic rate. So let's get started with the definition. Chemical kinetic is simply the study of how fast or how slow a chemical reaction is. This is a general chemical equation A. Using this as an example, reacting with B equals to form C plus D, where lowercase letters represent the coefficient in the balanced equation. The rate for this could be expressed as minus 1 over A, change in concentration of A over change in time, or change in concentration of B over change in time, or it could also be monitored as a function of product C, change in concentration of C over change in time, D as change in concentration of D over change in time. All these represent the rate of reaction. However, the rate of reaction also can be monitored as a function of two reagents A and B using what we call the rate law. Rate law is simply the mathematical equation describing how the rate of reaction changes with the changes in concentration of each reagent. Here is an example on rate law. If we have A and B, if we have reaction A and B going to C and D, we can say rate equals to rate constant times the concentration of A times concentration of B raised to some whole number integers, or sometimes can be fraction, where M and N represent the reaction orders with respect to reagent A, reagent B. This is a mathematical expression describing how the rate of reaction is progressing. You know what K is, that's the rate constant. M and N are reaction orders, which once you crunch the numbers for this lab, you will determine the rate constant, you will determine the reaction orders with respect to each reagent. How do you determine the rate constant? How do you determine the value for M and N? In this case, M and N, how do you determine? We use what we call method of initial rate. It is commonly used to determine the reaction orders. Here is an example. I'm going to use reaction between third butyl bromide with hydroxide ion, right? We will determine the reaction order with respect to third butyl bromide or 2-bromo-3-methyl propane, and reaction order with respect to hydroxide. Here is the question or questions we are going to answer is, what is the order with respect to hydroxide ion, and what is the reaction order with respect to third butyl bromide? And lastly, we will determine or write the rate equation or rate law for the reaction. This was one of the question in the quiz, therefore you can see the points here just coming from the quiz. So let's start off with by looking at the rate law. This is how the rate law will look like. Rate equals to rate constant times third butyl bromide, this is C, and then ER3 raised to some value. Let me call this M, times concentration of hydroxide ion raised to N, where M and N represent the reaction orders. So question A is, what is the reaction order with respect to hydroxide ion, How to proceed with this using the method of initial rate is, at the outset, we should have trials, either trial 1, trial 2, trial 3, or experiment 1, experiment 2, experiment 3. It could be even more than one experiment. In this case, we have 3 experiments: experiment 1, experiment 2, with respect to hydroxide. Here we have rate 1. I should have written that. If I have CH3C TR concentration of hydroxide here, ion, and then having the rate for each one. So we should have like 3 experiment. Here is trial 1. We call this trial or experiment 1, 2, and 3. And the concentration for experiment 1 for this is 0.25 molar, 0.50 molar, and this is molarity. And experiment 3, 0.50 molar. Experiment 1, concentration for hydroxide 0.25 molar, 0.25 molar, 0.50 molar, and the rate for each one of them here is 1.1 times 10 raised to negative 4, 2.2 times 10 raised to negative 4, 2.2 times 10 raised to negative 4. This is the rate in molarity. This is molarity per second, the rate at which the concentration is changing for experiment 1, experiment 2, experiment 3. You should understand that this is experiment 1 going across experiment 2, experiment 3. So how are we going to determine the reaction order with respect to each one of the reagent? In this case, here is the rate law. We want to determine M and N using method of initial rate. At the end of the exercise, you should complete the data table. I'll walk you through so that you have experiment 1 or trial 1, trial 2, trial 3. Let's proceed with termination of reaction orders. If we want to find M, all right, which is for M for hydroxide, it is N. Mag-U, we are using this N. So for N, this is N. You pick two experiments where the concentration of third butyl bromide is constant, or the first reagent is constant, but for hydroxide is changing. If I look at this, the concentration for experiment 1, experiment 2, or trial 1, trial 2, the first reagent is constant, but for hydroxide it is changing. Those are the two experiments we are going to use to determine the hydroxide, the reaction order with respect to hydroxide ion. Doesn't really matter whether you have rate 3 at the top, rate 2 below, or rate 2 above, or rate 3 below, so long as you identify everything for each trial in their respective place. For rate 3, everything for trial 3 will be at the top, everything below will be for rate 2. And remember, we are looking for hydroxide. This is for the first reagent. How this works is we assume that the 3 experiments were conducted at the same temperature. Therefore, rate constant will be same. In this case, we assume that K will cancel. Rate constant is always the same for all the experiments at the same temperature. With that, this will go away as well, all right? So if I cancel this and that will go. And if I cancel this will be 2 raised to n, 2 raised to n. 2 is coming from 0.50 divided by 0.25. So if I cancel this and that, this will be 1 equals to 2 raised to n. Remember, we are looking for value for n. Taking the log, this is something you need to know. Log of both sides, log of 1 equals to n log 2. Divide both sides by log 2, divide both sides by log 2. This implies log of 1 is 0, so 0 over log 2 equals to n, which means n equals to 0. The reaction order with respect to hydroxide is 0 order, 0 order. Therefore, the value, therefore, n equals to 0, n equals to 0. So remember, you pick 2 experiments where the concentration of what you are looking for is changing, the other one should be constant. We couldn't pick experiment 1 and 2 because the concentration for hydroxide is the same. In a similar fashion, we can determine the reaction of the rate, the reaction order with respect to third. We call this third bromide, or 2 bromo 2 methyl propane, just the IUPAC name for the compound. Nonetheless, let's see how to determine the reaction order with respect to these reagents. If you look at the experiments, since we already know for hydroxide, we got to pick 2 experiments where the reaction for the species is changing, the other one is constant, and turns out to be experiment 2 and 1. Experiment 2 and 1, and that is what we are going to use for determining the reaction order with respect to that butyl bromide. So it doesn't really matter again whether you have reaction 1 at the top or reaction 2 below. Switching it, you got to keep track of the concentration for each species. So just like before, the reaction order, I mean the rate constant will cancel, it's the same at the same temperature. We will cancel out the concentration for hydroxide. This is for hydroxide, it's the same as 1. And what will remain with is 2 raised to m, where m is the reaction order with respect to third butyl bromide or 2-methyl propane. So let's cancel this. This will be 2 equals to 2 raised to m. If we take the negative, the log for both sides, all right, m log 2, and divide both sides by log 2, divide both sides by log 2, it turns out that m equals to 1. So the reaction order is a fast order with respect to 2-methyl propane. So we have to determine the reaction order with respect to each reactant. Now the question is, part C, what is the rate law for this reaction? Remember rate law, assume this rate law is of this format, K, which is the rate constant times the concentration of 2-methyl propane raised to m, hydroxide raised to n. We need to find the rate constant. Here is the way to answer part C. First, calculate or determine the rate constant. Rate constant is K. This is K. At this temperature using any experiment. When we say any experiment here, it could be experiment 1, experiment 2, experiment 3 from our trials here. From our trials given here, 51, 52, 53. Let's use experiment. Let's see if it's experiment 3 based on the values I have here. All right, we can find the experiment 3 using experiment 3. All right, remember the reaction order with respect to hydroxide is 0, which means this one will just be 1. Any number raised to 0 is 1. Any number raised to 0 is 1, which means we will only use the rate for experiment 3 or trial 3, rate constant for trial 3, same raised to 1. If we multiply, all right, divide, not multiply, but divide both sides by 0.350, which is the concentration, turn out that this is the constant, and eventually the rate law. This is the rate law, this is the rate constant, and remember the rate constant is the same at the same temperature, whether it is trial 1, trial 2, trial 3. So we have used experiment 3 to determine the rate law, which is this. What is the rate law? We are looking for the rate law. First, we have to find the rate constant. Some questions you may be asked to find the rate constant only. Be careful, all right? So this is the kind of exercise you will do as far as this experiment is concerned. So now let's shift gears to part 2, which is completing the data sheet on page 81. On page 81, I will not read all this. Please go back, familiarize yourself on how to use method of initial rate to determine the rate law, to determine the rate constant. to determine the reaction orders. In this experiment, you are supposed to prepare a solution and run 4 experiments: trial 1, trial 2, trial 3, and trial 4. Trial 5 you see here is for the instructor, which I will use to show you how to complete the table on page, let's see which page, page 81. This is the instructor. I'll show you how these numbers were obtained. All right. And I hope you will also number your data sheet based on what I have on here, because down the line, I will walk you through how to calculate item or value for number 1, how to proceed with value for 2, 3, 4, 5, 6, 7, 8, all the way to 13 on the next page. So let's go back to table 1, how the data was collected. It was assumed that you have 2 test tubes, assuming that my markers here, this is A, this is B. Just assume that this is A, this is B. So with that, what I want you to imagine is this is for test tube number 1, the red right, not the green right here for number 1, and the red here is for test tube number 2. You are to mix the solution going across. This is trial 1, sodium thiosulfate. The concentration is 0.0010. In test tube number 1, 2 ml of sodium thiosulfate. This is the thiosulfate responsible for the reaction. Potassium iodide in test tube number 1, 2 ml. This is the concentration. For starch indicator, you use 20 drops, and remember 20 drops. All right, we did this recently. 20 drops equals to 1 ml. We will use this value in our calculation. So this is the solution in what? In test tube number 1 or test tube A. In test tube B, you are to have 0.040 molar potassium bromate, 2 ml of 0.1 molar HCl, and adding 2 ml of deionized water. So if you add these two solution, this experiment was conducted to see or determine how long will it take to see the color change. And the color change had to do with, let's see the calculation part so that you understand the times. On the calculation part, the reaction between thiosulfate and iodine will proceed, all right, until, look here, the reaction between thiosulfate will continue, but the color change is signified by the iodine reacting with starch. Therefore, the 20 drops of starch will react with iodine. The 20 drops of starch here, 20 drops of starch indicator will react with iodine, all right? And the color change signifying that thiosulfate has been consumed. And this means you have to stop the reaction. So pay in mind the times you see here, all right, which has been collected for you is the appearance of the blue color, right, which signifies that thiosulfate is complete and the reaction is complete, and then you need to record the time. So the times in seconds were based on the appearance of the color solution when you mixed it to reagent. Here In trial 1, you have to do twice, all right? In the first run, took 137 seconds, run 2, 135 seconds. You have to find the average, the average. Run 1, time for run 1 plus time for run 2, find the average and please show your work, okay? I don't want you just to put the value here. You should have a space for calculation. Where we will have here is for trial 2, okay? This is the time it took for trial 3, 72 seconds, for trial 4, 39 seconds. Now, for trial 5, which is the instructor, if we go back here, the reason why you have 310 is assume that, look, for the instructor, assuming that I took 2 ml of thiosulfate, 0.0010 molar thiosulfate, 1 ml of potassium iodide with this concentration, and 20 drops of indicator in test tube number 1. In test tube number 1. With the 20 drops of that. In test tube number 2, this is how I'm going across 1 ml of 0.04 potassium bromate to 3 ml of HCl. And the purpose of HCl is to give us hydrogen ion. You'll see this, all right, from HCl, is coming from HCl, just to give you posted on where H plus will come from HCl, the ionized water. So upon mixing the two, all right, upon mixing the two reagent from the data sheet here, it took 310 seconds to see the color change. See the color change. Now, for the catalyzed reaction, it's the same composition as run number 1. We all know what a catalyst is. A catalyst is a species which speeds up the rate of reaction, all right? And if you compare run 1 and this catalyzed reaction, it's the same composition. It's the same as what we have in trial 1 here. So these are the solution for trial 1, and these are the same solution for the catalyzed trial, but because of the catalyst, all right, it took shorter time or less time to see the color change, So with these values you have here, you will fill your data sheet, and then you will complete the table here. You will complete the table, fill in here, show the calculation, which will be now used to determine the reaction order with respect to iodide, ion, bromide, ion, bromide ion, and hydrogen ion concentration. And remember, this concentration right here and this one has nothing to do with the concentration you have here. I don't want you to assume that this is the concentration of iodide, this is the concentration of bromate, no? Or this is the concentration of H positive. I'll show you that on how you will proceed to find the concentration of each species in the final reaction mixture. First of all, how do we determine the rate of reaction? Are you going to fill these for run 1, run 2, run 3, and run 4? It will be a function of how you will see how this is done, all right? Let's see here on the whiteboard. What I have is, let's use instructor demonstration or instructor run here, okay? How did I end up with the rate of reaction is 9.77 times 10 raised to negative 8 molarity per seconds. There is in the background that all rate of reaction here, all reaction rate will be a function of change in concentration of the bromide ion over change in time. You took note of the time here is the time for the instructor to 310 seconds. This concentration here, it is for all the runs. This is the value you'll be using for all the runs for run 4, 3, 2, and 1. It's given in the calculation section. Let's see in the calculation section, there is a time here, change in concentration of bromide over change in time. Look here, the above value, that's change in concentration of bromide ion, is simply divided by the number of seconds in each trial to determine the rate of reaction for that trial. So remember, you will divide the concentration of bromide ion, which is this one, divided by the time it takes or it took to see the color change. In this case, for trial 4, 39 seconds, for trial 3, 72 seconds, for trial 2, you divide by 64 for trial 1. It's the average of the two. And please show your calculation for what? How you determine the rate of reaction. I don't want you to just copy and use your calculator and just put in the values. I want to see the calculation, which is pretty straightforward. It is the change in concentration of the bromide ion, which is this value, all over the change in time. This will take care of this column for rate, reaction rate in molarity per what? In molarity per second. You'll do the same thing for the catalyze. Remember, the catalyze is the same as run number 1. The constitution or the reagent for the catalyze is the same as for trial 1. So that's how you complete this. Now for the concentration of iodide, for concentration of iodide here for the instructor. If we go back to the instructor right here, look at the instructor. This is the potassium iodide, which means the iodide negative, I negative from potassium iodide. This is not the concentration you will use. You need to use the dilution law. You are expected to know the dilution law, M1 V1 equals to M2 V2, where M2 is actually the concentration of the iodide. I negative equals to M2 M1 V1 over V2. One thing you will notice that is if you add everything across, 2 plus 1 is 3 plus 1 is 4 plus 3 is 7 plus 3 is 10, but there is a 1 ml from 20 drop. Therefore, you divide all of them by 11 what? By 11 ml. In dimensional analysis, we cancel out the ml and ml. Will remain with the concentration. Will remain with the concentration of iodide, which is given 9.909 times 10 raised to -4. -4. This is how you find the concentration. That's how we ended up with this value. In case you're wondering how we ended up with this value, it is the concentration of initial concentration. This is M1. This is V1. Where is M1 coming from? From the table, from the instructor. The M1 is this right here. V1 is this, and then V2 is the total volume. You'll do the same thing for the bromide ion, okay? of which the concentration for that will be 3.6 4 times 10 raised to negative no, that's not where I want it. This is going to be 3.64 times 10 raised to negative 3 molar. Negative 3 molar. So this is the value here, concentration of bromide ion. Doing the same thing for hydrogen ion, M1V1. M1, this is the concentration of HCl, giving us the hydrogen ion unit analysis, and this also gives us 2.73 times 10 raised to negative 8. Okay, negative 8 molar. Please, you need to check, make sure that you have the concentration. Even in your data sheet, you'll also have these values. And please show your work the way I've just done here for each and every trial. For trial 1, how do you end up with the concentration of iodide? Concentration of what? Bromide. Concentration of iodide. Same for trial 2, same for trial 3, same for trial 4. Okay, and same for the catalyst. Once you fill or you complete this table, you will now have all the information to find the reaction order with respect to each species, with respect to iodide, with respect to bromine, with respect to hydrogen ion. And remember, just the way we did before, if we want to find the reaction order with respect to iodide, we'll have to pick 2 experiments where the concentration of the 2 are constant while this one is changing. If we want to find this should be the concentration of iodide should be constant, concentration of hydrogen should be constant, this one is changing. And last, to find the reaction order with respect to hydrogen, pick 2 experiments where the concentration of iodide and bromide are constant while the concentration of hydrogen is changing, and you use the method of initial rate to find the reaction orders, for each one of them. Now, so if you determine, once you complete the table, you'll be able to, you should be able to determine the reaction orders with respect to iodide or bromide and iodide using the method of initial rate. And also what? Determine the rate constant, that is K1, K2, K3, and K4. It's experimental. Okay. Let's see. Now, for item number 1 here, all right, I know I've numbered on the data sheet. There is 1, 2, 3. So for easy reference, in case you have a question, you can just say, hey, for item number 2, number 3, number 4, and so forth. It will be easier for remote assistance, or if you send me an email. Let's see, for item number 1, you want to compare the rate for the catalyze and the rate of trial 1. Remember, the constitution, the reagent were exactly the same, except that for the catalyze, there was supposed to be a catalyst, which is the molybdenum in this case. The rate here, all over the rate for trial 1. That is how you will calculate item number 1. For item number 2 and 3, they are the same. You will use the method of initial rate to find the reaction, to find the order with respect to iodide. In this case, let's see. For iodide, You will pick two experiments where the promate and the concentration of hydrogen ion are constant, but this one is changing. You will get the experimental, this is experimental order, all right? And then 3 here is the theoretical order. In other words, once you plug in the values, follow the method of initial rate, you will need to look at the worked example in the lab manual to differentiate those two values. The other one is just you have to round to all numbers. The other one you just leave it. For example, here, this is where I want to highlight the difference between experimental orders and the theoretical orders. If the experimental value is fraction, just maintain the fraction. For the whole number, you need to round it off to whole number. Here is 0.68, round up to 1, 0.41, you round off to 0. If it is 1.5, 1.6, 1.78, 1.9, you round up to 2. So experimental will be fraction, theoretical will be whole numbers. Please read on page 85 on how to determine the experimental and the theoretical. That is what you need to do in what? In finding the values for experimental. Here at the top is experimental. That's what I have here. At the top is experimental. 3 here is the theoretical. This is fraction. See, it is fraction. Fractional. Yeah, it's gonna be decimal place, and this will be all integers. It's gonna be all integers for bromide ion and for iodide ion. So once you have the experimental and theoretical rate orders, all right, you will determine the rate constant for experiment 1. For experiment 1, it's gonna be rate 1, which you have equals to K1 experimental. That's the experimental times concentration of iodide all right, concentration of iodide. Let's call this X times concentration of bromide ion, 3 negative, raised to Y times concentration of hydrogen ion raised to, this is raised to, let's say, XYZ. So here, I was just showing you how to find item number 4. How do you find experimental? This will be experimental right here. Value. So if you like experimental values here, you'll get the experimental rate constant. You'll do for trial 2, you'll do for trial 3, you'll do for trial 4. And remember, K here, okay, K equals to, and this is experimental, is rate 1, which you should have rate 1 of for trial 1, what is the concentration of iodide raised to experimental value times bromide ion BOR3 negative raised to Y concentration of H plus raised to Z. This is for experimental exponent, for experimental. This is for 1. You'll do the same for 2, 3, 4, and then you find the average of experimental rate constants. So you add the 4 divided by 4. Now, theoretical, that is item 5 here. The only difference is you will do what? You will use the experiment theoretical. So here is item number 5 here, where X, Y, and Z are theoretical orders with respect to each species, all right, with respect to iodide, bromine, and hydrogen ion. Just like in trial 2, you'll do the same thing. Trial 3 and trial 4, there will be K2, K3, K4, then add the 4 theoretical rate constant divided by 4 to get the average. Now, theoretical rate law, right? Use the whole numbers, which will be of this form. K is just K times, you need to use whole numbers here. Positive, there is PRO, negative, and then I negative. So you'll use all numbers for X, Y, and Z. These are X, Y, Z. Is use all numbers. Write your what? Write your rate law. For number 6, rate law. For the equation, use the whole numbers. For exponent, which is 3, for bromide here, and for iodine. In writing the rate law equation. Now, there are some slight changes here. I'm using an old fashion of the lab manual, but when we say experimental, everything should be experimental, not theoretical. When we say theoretical, everything should be theoretical, not experimental, or swapping the terms here. Let's see number 7. On my whiteboard here, number 7, calculate the experimental rate for trial 5. That is for trial 5, which means we are using rate 5. This is going to be rate 5 equals to K, which is the average experimental. This is experimental average experimental times X experimental bromide ion times Y experimental, then hydrogen ion Z experimental. So everything is experimental. This is the predicted rate of reaction 5 right here, using the experimental average, all right, and using experimental rate reaction orders, using experimental reaction orders. So here you'll have to use for trial 5. For the theoretical, it's the same. This is for 7. For 8, let's look at 8. For 8, it's the same thing, except we are using the trial 5. So if I write rate 5 which you should have on the table times K. And this now is theoretical average. All right, theoretical average K times concentration of iodide raised to X, concentration of bromate ion raised to Y, concentration of hydrogen ion raised to Z, where X, Y, Z are theoretical. X, Y, and C, these are theoretical. They are theoretical. All right, theoretical. So the difference between this is experimental. It's got to be fractional exponent. So we switch that fractional exponent, and this one got to be all integers. All right. Now, once you have item 7 and 8, for item number 9, which is the next page, I believe, yes, page 82 in your text or in your lab manual, item number 9, percent error experimental determined value minus experimental predicted value over the experimental predicted value. So experimental, you have to find the absolute value. Whichever is bigger, just change to positive. So line 7 for item 7 minus item 8, absolute value divided by 8 times 100% for line 9. Now, one of the factors which affect the rate of reaction is temperature, and there were two trials, or there were two temperatures, sorry, there were two temperature water bath in the lab, which were to monitor the rate of reaction at 35 degrees Celsius and at 50 degrees Celsius. And the numbers here you see is the time it took for the color change to happen. You see that at 50 it took less time, 35 it took less time. However, it's not as in at room temperature, which is around 23 degrees Celsius. So in 35 degrees Celsius, we used to do twice, forget about the average time. This is the only time we have, so just going to use this. And to find the rate of reaction for 10 and 11, was just at elevated temperature, you'll use this equation. Look at what I have for 10 and 11. It's just a change in concentration of bromate ion over change in time, or just over time. And for 35, 62 seconds, and at 50 degrees Celsius, 40 seconds. Just divide the two and get the rate of reaction. Lastly, for 12 and 13, the difference here is, all right, percent rate increase, rate of reaction at elevated temperature over rate of reaction at room temperature. This was for trial 1, room temperature. For this percent increase, the constitution or the solution for trial 1 was the same as the solution for elevated temperature. You will do this twice. For 13, you're going to use the same equation. For 12, same equation. 13, same equation. And you should have rate for trial 1 from the table. Rate for trial 1. This is the rate for elevated temperature, and then the rate for trial 1 is right here. And of course, you want to know the percent, what you're gonna fit in there, and have the percent increase, or the percent increase for that. That will complete all the points in multiply by 100. And with that, I want to just wrap up by saying show all your calculation for each item. Please number them. I'll be going through the checklist. That do you have item number 1? Do you have item number 2? Do you have item number 3? All right. If you don't have all the items, and then it will be very difficult to proceed with evaluating. Other than that, I want to say thank you. I'll stop sharing my screen. Please submit the lab report by the posted